Good morning, everyone. Attention, please. We're about to start now. Yeah, sorry, it's me again. The bad guy who always, cut your talk conversations, but it's time. We have to start now. So our third speaker this morning is Dr. Adnan Rajib. He's a tenure track assistant professor and the director of the Hydrology and Hydroinformatics Innovation Lab in the Department of Civil Engineering of University of UTA. And Dr. Rajib received his Ph.D. in civil engineering from Purdue University in 2017, and he became a postdoctorate scientist at the US EPA during 2017 to 2019. And in his 4-year service as a tenure track faculty, Dr. Rajib has secured several competitive federal grants as a principal investigator, such as from NASA, NSF, Department of Defense, Department of Agriculture, and Department of the Interior. And his work has been published in reputed journals, including the Nature and the Nature Scientific Data. And this morning, Dr. Rajib will give us a presentation on the flood, satellite data, and the AI, which is very interesting. So without further ado, let's welcome Dr. Rajib.
Better now? That was a long introduction. Um, I don't see my slides here yet. All right. Thanks all for joining my presentation. I'm Adnan. I'm an assistant professor as well as the director of the Hydrology and Hydroinformatics Innovation Lab at the UT Arlington Civil Engineering. Today I'm going to talk about a new paradigm about rethinking or redefining flood risk in Texas in the era of satellite data and AI. This is very timely because AI has been mandated as through the new executive orders, AI has been mandated as the new frontier of research and application for water infrastructure and civil infrastructure in general. So that's why I'm tagging this as a new paradigm. Next. Um, but first, I would like to acknowledge my team. We are a large, self-reliant team at UTA Civil Engineering. We call ourselves Hydrology and Hydroinformatics Innovation Lab. We have around 8 PhD students, postdocs, undergraduate research assistants, and to your surprise, we also have a fully funded high school research assistant. And we have been fortunate to garner some promising federal funds through NASA, NSF, USDA, Department of Defense, among others, all focusing towards some top priority projects on national water security. Um, Next. All right. Before we get into the details, let's take a moment to understand the problem here. There's no doubt Texas infrastructure is flood susceptible. However, there has been numerous state and local level public and private initiatives to avert this problem, but there is a critical data gap. And these data gap is hindering the efforts to enhance the state's resilience. And my presentation is all about merging that data gap using new generation satellite data and artificial intelligence. Next. All right. So how do we rethink or redefine the flood risk of our state in the era of satellite data and AI? I'm introducing 5 thrust areas. These thrust areas could be the template for us to discuss collaborations and kind of outline the future pathways. The thrust areas, the first one is AI-based flood mapping at hyper resolution at street levels or address point levels. Second tertiary is about near real-time flood depth or water depth mapping. Third one is my favorite. How do we track developments or urbanization within flood zones? Um, then the fourth area is about nature-based solutions. This is a really new buzzword used by lots of federal agencies, and wetland loss and using the wetlands as storm retention structure is the essence of this third area four. And I will end my talk with a new idea of hyper-resolution land cover mapping. The common theme across all these trust areas is the power of data, geospatial technology, and computing to deliver fast and efficient information to the hands of the practitioners and the people. Next. All right, the first one, AI-based flood mapping at street level and address point level. Um, this is a map for a small portion in Houston, Texas. And all these colors indicate flood susceptibility. I'm going to explain how did I use AI and satellite data to come up with this so-called colorful flood susceptibility map in a bit. But before I do that, let's have a closer look on at the map here. Of course, the colors are self-explanatory. The red means more flood susceptible. However, uh, I also overlaid the 100-year floodplain maps on the flood susceptibility, the AI generated flood susceptibility map. Um, and also I overlaid the critical infrastructures like hospitals, power substations, fire stations, and all that. There are two takeaways from this map. First, the AI generated flood susceptibility map follows the floodplains, number one. Number two, there's a lot more flood susceptible areas outside the so-called 100-year floodplain. That tells floodplain itself is not an adequate indicator of flood risk. So we have to go beyond floodplains. And that's the essence of street level and address point level flood mapping through AI and satellite data. Next. Now, I'm going to explain how did we produce this so-called flood susceptibility map. It's a common sense approach. What makes things flood susceptible? If you are on a high ground, you are less susceptible. If you're on a low ground, you are more likely to be flooded. So there is topography. Um, Distance from the stream, how far you are or how proximal you are to the stream that determines your flood susceptibility. There's also land cover, and more interestingly, that's my favorite, the history of inundation. You have satellites that are taking pictures since 1970s, and from those satellite pictures, you can track the history of an area getting inundated. If you find out an area that has a history or a track record of getting inundated again and again, it's more flood susceptible. So that data is available for free. So this common sense approach leads to this flood susceptibility mapping. What we did here is we um, tracked all these different data sources and we stitched them together using a very user-friendly artificial intelligence, and that led us to this flood susceptibility map. And you can tell there is not just um, um, specific floodplain zone here. As long as you have a land surface, we are able to identify flood susceptibility for the entire land surface. It's not specific to a particular zone of flooding. So that's the beauty of it. And then um, if you zoom in, you can find out that, yeah, it matches the floodplains, but also, as I said, there's a lot more areas that are flood susceptible outside the floodplain. Next. All right. Here, we downloaded the data from Department of Homeland Security. These locations are individual critical infrastructure locations. The first one is the power substations in Houston, then hospitals, then fire stations. We are able to identify the flood susceptibility indicator, or just which is just a value, by the way. If you get closer to 1, you are more vulnerable. So we are able to identify the flood susceptibility for each of these infrastructure, for each of these power substations or hospitals or fire stations. So this is a step change from our lumped regional assessment of risk. I hope you see what I'm saying here. Now, what I did next is, after I identified the flood susceptibility of this infrastructure, um, I tried to identify how many of these flood susceptible infrastructures are within our traditional floodplains and outside our floodplains. So those bar diagrams at the bottom of our slide indicates that the red ones means the flood susceptible critical infrastructure that are within our commonly used 100-year floodplains. What you can tell from these pictures, um, only a small portion of flood susceptible critical infrastructures are within the floodplain. There are many critical infrastructures outside the 100-year floodplain that can be flood susceptible. All right. Next. All right. Um, Based on those early successes of uh, determining flood susceptibility at address point level, we um, further analyzed flood susceptibility at street level. As long as you know the road network, you are able to identify the flood susceptibility of the road network as well as the other critical infrastructure that are adjacent to the road network. Here, I'm just showing a zoomed in map of southern Houston and all the power substations near or proximal to the road network. Again, the color and the size of the bubble indicates flood susceptibility. The take-home message from these pictures is we can harness the power of open source data to identify flood susceptibility at very fine resolution and with local relevance like address point or street level. The good thing is we can also rank the infrastructure, because as practitioners and engineers, we always need to have to tell people that this is the more vulnerable, that is not, because there's always cost associated with it. So we can rank the infrastructure, and most importantly, this is a fast and automatic approach. It's not rocket science. Everyone is using the AI these days. So it's fast and automatic, and it can be applicable anywhere. Even though I showed maps for Houston, it can be applicable to this building or to Dallas Fort Worth in general, anywhere in the state. Next. All right. Next, I'm going to talk about near real-time flood depth mapping. Um, I have the opportunity to work with many small localities across the state where there's a need for early warning system. There is one caveat though. Yes, there is a lot of progress towards early warning or flood forecasting system across the communities in our state. All these existing flood warning system falls short in terms of their capability. Most of these early warning systems are for inundation mapping. The capability to predict flood depth or water depth in near real time, it's lacking. And of course, you understand that it's not the area of the flooding, it's the depth of water, which is a better indicator of risk. Now, to explain that, here's an illustration of our results for Austin. And the second picture, you can tell from the second picture that the blue area is the inundation for a given flood event. And all those yellow boundaries, these are the buildings. We are able to identify the building footprints. This map triggers a question. Are all these buildings having the same level of risk because they are within the flood inundation zone? The answer is not. So this is a very strange idea. If I am in a flood zone, I am vulnerable. If I am just outside the boundary, I am safe. It's not real. So that triggers the idea of flood depth based risk mapping. The third picture is where We again superimpose all these buildings and superimpose the flood depth. Now you can tell that not all the buildings are in the same water level. Okay. The question is next. The question is, how do we predict flood depth in near real time? So we developed a tool that uses any inundation extent. You have a model, you have flood inundation extent from your HMS or HCRAS, and we can just take any flood inundation extent and plug in that flood inundation extent, and that's it. We are able to generate flood depth. The difference here is that if you are relying on traditional models like HCRAS or other hydrodynamic models, it takes time. It takes time and computational resources, and many industries or many communities, they do not have that type of resource or manpower at the time of that hazard. At the time when there is flooding, you don't have the time or the mindset or the resource to run HCRAS and generate flood depth maps. That's a problem. However, as long as you have an inundation extent, either it can be from your model or from satellite pictures of inundation, that's the only thing we need. We are able to generate flood inundation depth or water depth in near real time. We tested our algorithm across different locations within northeast and south central United States. These colorful maps, these are for specific day of the flooding. We captured the picture of the water, flood water from satellites, and we generated the flood depth for that particular day of the flooding. Next. Now, of course, this is a step change from our traditional mindset where we are almost always over relying on HCRAS or such or similar models. The obvious question is, how accurate is our AI-based flood depth tool? So here is an assessment for, again, for different parts of the country. One location is in San Antonio, the others are in different states. The first column is our flood depth. Second column is USGS database. USGS has a FEME flood inundation modeling database, which is based on survey data, HCRAS modeling, bathymetry, all sorts of things. So the second column is our kind of our reference, and the third column is the difference. The advantage in our approach is that it's less data intensive. So we, as I said, we can generate flood depth for any given inundation extent, potentially in near real time. Of course, there could be lag of 2 to 5 days. That's why it's not real time, it's near real time, depending on how long it takes for us to collaborate with one of the industries to get an inundation extent or downloading the flood map from a satellite. The second advantage is that it's only requires topography and other existing databases. So this tool does not replace existing data sets that have been generated through years, like BLE or FEMA's flood maps. It does not replace. Rather, it takes those data sets as one of the inputs and further enhances itself. And speaking of topography, not all the areas have LiDAR, so that's fine. Any given topography, it runs. And most importantly, it does not require sophisticated data sets such as river bathymetry and all that. Again, going back to the comparison, the first column is our model, no bathymetry, nothing, just given inundation extent and topography. You can tell that it's matching the USGS reference fairly well. Next. All right. So this is my favorite thrust area. Often when we talk about tools and models and flood risk, our thoughts and ideas get submerged into a single tracked or one-dimensional question. And that question is, how does floods make human vulnerable? Or how does floods increase human risk? But there is another dimension to that question. How does how do humans increase flood risk? How do humans increase the vulnerability of the floodplain? So this is a question that we usually do not answer. So our team developed a new approach to assess or predict how human development is altering the floodplains and thereby increasing the flood risk. And it was this is a screenshot of a news article that was published by Nature Outlook at London, UK last year. Next. All right. So the question here is, how do humans change the floodplains and increase the flood risk? These are um, three examples for three major cities in Texas. I'm not sure whether you can see those color blobs here, different types of changes, whether or not a forest got converted into agriculture or whether or not a ranch got converted into a developed area within the floodplain. Those gray areas are floodplains. Um, Next. So using history of satellite observations and artificial intelligence, we created this time series. From 1990s until present here, we tracked how the floodplains are being developed over time across three different cities. And what surprised me here is the trend of Dallas-Fort Worth. You can tell from for the recent years, it's almost endlessly increasing. The floodplains in Dallas-Fort Worth almost endlessly being developed. Surprisingly, Houston is showing rather a moderate trend. It's probably after the aftermath of Hurricane Harvey. There were a lot of awareness going on, so that's why the trend of urbanizing the Houston's floodplain, it's rather mild. And Austin, almost same as Dallas Fort Worth. So it also tells the human mindset. Unless we are stricken by a mega disaster, we don't learn. So again, looking at these trends. By the way, the trends here identify how much area within these cities are getting altered by human development. How much area within the floodplain. um, uh, Dallas Fort Worth, we are losing almost 1 square kilometer of floodplains every year due to human development. So these are critical considerations that we need to take into account when we design stormwater retention structures, or as practitioners when we implement conservation policies or planning tools. We need to take into account these numbers. Next. All right. Um, A relevant topic with floodplain alteration is nature-based solutions, how we can make room for water through nature-based solutions. And speaking of nature-based solutions, aligned with floodplain alteration, there is also wetland loss. I'm not sure you guys know that Texas was a big wetland in dinosaur age. And if you go to Big Bend National Park, you see there's like lots of illustrations showing how the entire state was a floodplain or a coastal floodplain or just watery marsh, the entire state, and it was the home of the dinosaurs. It was full of wetlands. However, now we are here in Dallas, 14 in 2025. We don't have floodplains left, and also we don't have wetlands left. So these are the two comparisons of Houston area. The first one is the present day wetlands. All the blue dots, these are wetlands in Houston. We used satellite data from 1980s and used AI to map which ones were there in 1980s and eventually disappeared. And the colors are self-explanatory. Again, these are pictures. Pictures don't lie. And we found out that those red areas in Houston, they were wetlands in 1980s, and now they're gone. Again, if I zoom in super close, I can find a dinosaur-shaped wetland somewhere in Houston. Now that dinosaur is gone, there is a parking lot. Okay. So the essence here is using data and AI, we can find out the lost wetlands, and those lost wetlands could be incorporated in your planning tools when you are designing stormwater retention. Something that we usually do not consider. Also, another factor that we do not consider is the history of the loss or the rate of the loss. When we are designing new stormwater infrastructure, we are not designing it for today. We're designing it for next 50 years or so, or whatever. So we need to take into account how much water can be stored, and are there any natural storage hidden in our landscape? So these type of tools help us kind of enhance our existing stormwater retention design. Next. All right. So to help this nature-based stormwater retention design, my team developed this first AI-based potential wetland map for the state. And because these are potential, we don't know for sure whether or not this particular area is a wetland. So we converted this into a probabilistic map, 0 to 100%. The more red means it's highly likely that there is a wetland or wetland type soil that you could use for your stormwater design. And we leave it up to your engineering judgment to decide whether or not you are going to use that area as a potential stormwater retention site. The advantage is that um, it's very high resolution, 30 meter. So it gives you more room for your judgment. And also, it's very much aligned with US Army Corps' Engineering with Nature initiative. Also, it can, as I said, it can improve the traditional stormwater retention design as long as you know that where the wetlands are. And the maps A, B, C, D at the bottom left, it shows that these data sets are extremely high resolution, less than 10-meter resolution. So you can harness the power of data to generate stormwater retention design at a very localized resolution. So that's the key message here. Next. All right, this is my final thirst area. So we talked about lots of things like flood risk, flood depth mapping, then human alterations of the floodplains, then new paradigm of stormwater retention design by finding the lost wetlands. But all of these at the core depend on land cover. And land cover is not specific to water. It's in general helpful for urban planning or engineering decision making. So I'm sure you know that National Land Cover Database, it's kind of the gold standard. All the tools and decision making are dependent on National Land Cover Database. So here, again, another example for Houston, the red map is NLCD, National Land Cover Database. All red, of course, this is Houston. Then I compare aerial imagery. Taking the pictures from the satellite, I compare the aerial imagery. The problem here is uh, National Land Cover Database, even though this is the ground truth, it lacks details. I'm going to explain in the next slide. Next, please. All right. So here, I'm comparing NLCD with the aerial imagery. Let's just follow the numbers 1, 2, 3, 4. 1, according to NLCD, is a low developed urban area, according to NLCD. But according to aerial imagery, that's water. Then number 2, which is highly developed patch of land, according to aerial imagery, that's basically an open space within an apartment complex. So these differences are important because urban floods are not the same as riverine floods. Urban floods occur in small patches, and if one of our major input is incorrect or lumped or aggregated, it's highly likely that those small patches of flood, whatever we are predicting, those will be incorrect. Now, how do we? Again, we are being encouraged to use 1 meter LiDAR, computationally intensive, time consuming 1 meter LiDAR for our flood mapping. But at the back end, we are relying on 30-meter National Land Cover Database. That doesn't make sense. Okay, so going after fine resolution, sophisticated data does not always give you the best results. So this is one example why that's happening. So the question is, how do we merge this gap? Can we go beyond National Land Cover Database and predict land cover in very fine resolution, small patches? The answer is yes. Next. So I'm introducing explainable AI. Um, for many of us, AI is a black box, and it's we think that it is going to replace our understanding. But my mindset is, no, we are smarter than AI. So that's where the explainable AI comes into picture. Explainable AI uh, allows us or humans to tell the AI that, hey, this green that you see, this is not a forest, this is just a park. Or the green that you see, this is just a football field. That way, you are intervening the AI and making it more realistic. So, under this new explainable AI, I'm proposing new classes of land cover. For instance, in National Land Cover Database, you have highly developed, low developed, those type of not so explicit land cover classes. What if we transition to industrial, commercial, parking lot, roads, bend, those type of like that? Those are more meaningful, right? Same for forest classes, we can replace that with park, open space, and so on. So this is something that can really make us a net change in our current flood mapping practices. Next. All right. So what is our take-home message? The AI data provide a fast and efficient solution. It's not going to replace our existing efforts. Rather, it's designed to enhance our practice and our existing efforts. And the power of AI can help us fill data gaps and address emerging problems. And the 5 thrust areas that I presented, it could be our template for discussions for more funded and unfunded collaborations. And I'm always there to help. Um, and you have my email address here, and feel free to send me an email if you want to talk. Thank you very much.
Thank you for, you know,
Um, So yeah, that's a great question. The question here is the AI generated flood susceptibility maps. We found that they are following the 100-year maps, but there are a lot more susceptible areas beyond that 100-year zone. So the question is, what if there is a 500-year maps or a 100-year, 1,000-year floodplain map? Is our flood susceptibility map going to match with that 500-year and 1,000-year flood maps, right? The answer is yes or no, both, because not the entire landscape is a floodplain. So riverine flood mapping has a limitation. It follows the river, but in areas like DFW or Houston, where you don't have a distinct river network, you don't get to see floodplain maps. But that doesn't mean that we are not getting flooded, right? So that's why this flood susceptibility map helps us replace or supplement the idea of floodplain maps. Yeah, yeah, yeah. Yes, we verified our flood susceptibility maps for Harris County flood control districts datasets. They have like 100-year, 500-year, and 1,000-year floodplain maps, as well as Hurricane Harvey and some other recent storm events. We found that those big storms are all over. They're flooding all over the place. It's not following a floodplain. So we use both existing jurisdictional floodplain maps as well as those satellite observed flood inundation maps for those big storms, and we found high correlation. Yeah, no problem. Thank you very much.